Most of you are familiar with Jeff, research scientist at the Research and Outreach Center, soil scientist, the steward of the drainage plots that were started by Giles years ago, and he is going to be talking about the most recent research going on there.
All right, as Brad said, I'm going to focus this talk on just one study that we're doing at the Research and Outreach Center on our drainage research facility. So it's similar to what Fabian talked about earlier, but at Waseca. So we're looking at cover crops, nitrogen rates, and different cropping systems and how they might affect nitrogen loss in tile drainage water and corn production. And it is in continuous corn. So we know that cover crops have been proposed as a significant component of nitrate reduction strategies, not only in Minnesota, but throughout the Midwest to try to reduce nitrate losses in both ground and surface waters. But as Jeff Strock mentioned today too, they don't work all the time. And one of the farmer panelists also talked about after full season corn and soybeans, sometimes you have a struggle getting that cover crop established. And this was a study that ran on the exact same site at Waseca from 2017 through 2020. And we had 1 year where we had pretty decent cover crop establishment. And this was overseeded or simulated broadcast seeding while the crop was senescing in a corn bean rotation. And that year, where we had decent establishment, we had a nice reduction in nitrate concentrations in tile drainage water. We're here with the cereal rye. The blend of annuals that froze out in the winter were kind of intermediate, and the no cover crop was up here. But all the other years or all the other periods where we had drainage, we did not get great cover crop growth, and we did not get that beneficial water quality effect. So what I decided in this next kind of go around of this study was, let's focus on placing these cover crops in production systems where they're likely to thrive. Thereby, they'll improve water quality, hopefully. And then Anna Cates has been working with me looking at soil health and how these practices might influence soil health as well. So thinking of cover crops, as Jerry Grosskreitz mentioned in the farmer panel, thinking of cover crops after these short season crops, whether it's peas, sweet corn, small grains, and in this case, I'm going to look at corn silage. Seeding a cover crop after corn silage harvest can scavenge nitrate, which is obviously what I'm going to focus on today. But it also can protect the soil from soil erosion because obviously after corn silage you have very little biomass left in the field and very little residue. And hopefully maybe even might be able to mitigate some of the carbon loss in a corn silage system. And then of the 8.5 million acres of corn in Minnesota, about 450,000 are harvested annually for silage every year. So if you just did these corn silage acres, the sweet corn acres, the pea acres, that's a significant component of those acres of those early season crops in the state of Minnesota. So our research questions for this study are to look at the nitrate concentration and loads in tile drainage and to see if they're different between corn grown for grain and corn grown for or harvested for silage. And I looked in the literature and I really have never seen this compared or studied in any other study. Usually if they look at silage, they just focus on silage. They don't also have corn grain treatments. So that was something novel that we haven't done and it hasn't really been done in the Midwest. Also, we wanted to look at see if spring terminated cereal rye is going to provide superior water quality benefits, and we suspect it will, compared to something like a group of annuals like oats, forage peas, and tillage radish, which are easy to do. They terminate themselves, so it's a little easier management, but they're also not, they don't stick around till springtime, which is critical because that's when the drainage period is. And we're also going to look at the effects of economics, the interactions between nitrogen rate and these cover crop species and when they're terminated. And we also are looking at silage quality, nitrogen loss, and uptake in NUE, and don't have enough time to cover all these things today, obviously. So these are the treatments, and I turn my pointer on here. You can see that. So there's 11 treatments, but the core treatments are these first 9. They all have tile water monitoring. So there's a individual tile that goes to each of these plots, and like Fabian said, they're lined with a perimeter plastic lining, so hopefully there's minimal lateral flow between the tiles. There's one perforated tile that goes into the plot, and that collects the water. It goes into a culvert. We measured the volume And then we take a flow-weighted subsample to get the nitrate concentration. So these first 9 treatments all have that tile water monitoring. The first 3 are corn grown for grain. They have no cover crop, and it's at 3 different N rates. 4.6 pounds is our control or 0N. It gets 4.6 pounds from starter fertilizer, but that's basically 0. 180 and 220 pounds of N per acre for corn after corn. Then we have corn silage grown without a cover crop at those same 2 N rates, 180, 220 for a total N rate. Corn silage with cereal rye, same N rates. Corn silage with this blend of annuals at those same N rates. And then we have 2 additional treatments that are corn grown for grain with different N rates, just so we can better have an idea of what is the optimum N rate for corn grown for grain at this site. The nitrogen timing or application is we only put on 20 pounds of N with the planter at planting time. There's no pre-plant, no fall applied N. The rest is applied as kind of an early side dress as stream injected UAN. We use a strip tillage system. So this split application of some at planting and some as an early side dress is a good system for this strip till system. The cover crops were seeded at 60 pounds of rye per acre in the fall right after corn silage harvest, and that's with a drill, no-till drill. And the oat, forage pea, and radish is 15, 8, and 1 pounds respectively. So the next 3 slides are just some pictures to kind of give you an idea of what this study is like and how it works. So this is a schematic of the drainage study. We have these culverts, and there's non-perforated pipe that runs to each of these tiles, and there's a perforated pipe inside that plastic perimeter that collects that water and drains into the tile. Once it's in the tile or in this well, it collects in another well. It's pumped by a sump pump, just like you have in your basement of your house if you live here in South Central Minnesota, and it goes through a water meter, measures the volume. Once the pump kicks on, it results in pressure, which pressure puts us a little bit of water in a collection tank, and we collect those samples twice a week when it's flowing regularly and just once a week when it's not flowing regularly. So the study initiated in 2021. It was corn after beans that first year. We had fixed N rates that we applied that coincided with the treatments that were going to come in the future. We went out there and we cleaned off the plots with the silage harvester. We no-till drilled the rye on the same day, or the cover crops. This is what the cover crop blend looked like about 6 weeks after planting, and this is what the cereal rye looked like. We took biomass yields from those cover crops, and then we do fall strip tillage, and then the next spring we terminate the cereal rye about 10 days to 2 weeks before planting, and we plant corn. And of course, the annual blends, or the blend of oats, radish, and peas, they die from cold temperatures, and you don't have to terminate those the next spring. So this shows that. Here's the cereal rye come springtime in April, about the time we were going to take cover crop biomass samples and terminate it. Here's the residue that's remaining from the oats, radish, and if you didn't have a plot plan and didn't know which treatments were these, it'd be very difficult to find it. Here he shows us planting in May 19th. We're expecting to plant in the first week of May, but weather delayed that. We didn't intend to plant green. You see some rye residue there, or some rye cover crop. We actually sprayed it around the 23rd of April or 22nd of April, and it was a nice day the day we sprayed it, but the next 5 or 6 days was cold and wet, and it didn't kill all of it. So we actually had to spray it again in early May to kill it. And then we side dressed on June 9th that first year. This was the second fall, or so the fall of 2022. We did not get very good growth. If you remember that year, it was extraordinarily dry. We did get one little shot of rain that allowed some of the cover crop to germinate, but it was so dry it never really thrived, didn't grow very well. We had very patchy stands. This is what it looked like in the spring, where the cereal rye was. We did the strip till, we planted, we burned it down, even though there wasn't a lot of material there, and we side dressed. The last fall, the fall of 2023, it doesn't look like we had great growth there, but we actually had very good stand. It just didn't get as tall because, again, it was a drier fall. But you see where we did our strip tillage, And this is what the cereal rye looked like come springtime. You can see our zones where we did our strip till where we're going to plant. And in between that, there's pretty good rye cover. And after we burned it down and we're planting, this is kind of what it looks like. So looking at our rye cover crop biomass, and this is dried for 3 or 4 days in forced air dryer. So it's truly dry biomass. This is the first fall. We had about 296 and 255 pounds of biomass between the cereal rye and the annual blend. The next spring, our cereal rye was about the same. So recognize it did grow some, but when the strip tillage occurs, we do take some of it out. So it ended up being about the same. The fall of 2022, we had such poor growth, we couldn't really collect biomass samples. We did in the cereal rye that next spring, but it was only 28 pounds, so it was virtually little or nothing. The next fall of 2023, we had good growth. The annual blend actually grew much better than the cereal rye. This last spring, 2024, it grew substantially in the springtime, which isn't surprising because we had such a mild winter and a fairly early spring, especially late February and early March. So we were up to our greatest amount of biomass that we had in any period, and that was 676 pounds in the spring of 2024. And then this last fall, we were at about 75 to 65 pounds. So we had decent germination last fall, but not an extraordinary amount of growth. Down here at the bottom, we have the carbon to nitrogen ratio of the biomass, and you can see that it's ranged anywhere from in the mid nines or upper nines to about 12 and a half part per million, or carbon to nitrogen ratio. And generally when we're in those lower values like these, this is biomass that's going to degrade fairly rapidly and is probably not going to tie up or immobilize nitrogen. We took soil samples both in the spring and in the fall. I'm just going to show the fall stuff for now. The spring stuff, we're still looking at some of the soil health measurements for the 2024 samples, but we have all the 2022 and 23 data. Generally, I would say the spring samples, we're looking at more depths and greater depths. And when I glance at them, I see some differences in nitrate concentrations, but all the other parameters we're measuring, I don't see what I think are going to be significant differences. But we haven't done all the statistical analysis of that data. But when we look at this is fall, late fall, like in mid-November or early November, right before soil freeze up, this is kind of looking at nitrate and ammonium to see if the cover crops have scavenged any nitrate compared to the non-cover crop treatments and how the cropping systems compare. So this was the fall of 2022. Here's our control treatment for nitrate. Here's our 180 and our 220 pound rates across the 4 different cropping systems: grain corn, silage corn without a cover, silage with rye, and silage in the blend. Over here are the means across cropping systems, averaged across N rates, and you can see that the grain corn cropping system is much lower than the silage with rye or the silage with blend, and there's really, in this year, there's no difference, which is probably very understanding because we had very poor cover crop growth that fall, so we wouldn't expect the cover crops to affect residual nitrate or the amount of nitrate left in the profile. But what you do see is much greater nitrate in the silage systems compared to the corn grain system. And that can be related to the fact that the silage is harvested earlier and you've got time for mineralization of nitrogen before it gets to that late fall sampling. And then also you see that the 220 pound previous rate generally had higher nitrate than the 180. When we moved to the fall of 2023, this trend with the grain corn being much lower is still there. There's some differences, numeric differences here among the silage treatments, and that year we had better growth of the cover crops, but there are no significant differences. The 11.5 part per million is basically the same as 15.6 according to the statistics, and of course this is 0 to 1 foot depth. There were no significant differences in ammonium nitrogen in the study. So we'll talk a little bit about yields. First we'll look at corn yields and then silage. So over here we have corn grown and harvested for grain. There's no cover crop in these. These are our 5 nitrogen rates from our control of 4.6 pounds up to 260. These are our 3 growing seasons. In 2022, we had yields that started at about 60 pounds with the control, or 60 bushels went up to 218, and it took that highest N rate to optimize production. In 2023, our control yielded only 48 bushels. We increased up to the 220 and the 260 to statistically were the same. They both have a letter A, but you see that the yields are slowly trending upward. That was a year that was fairly droughty, and we did not have as good a corn yields. 2024, our control yielded about 84, went up to 227, and again, anywhere between 220 and 227 seemed to or 220 pounds of N and 260 optimized production. Keep that in mind as we look at the silage yields. So for the silage yields, you can take silage yields from corn grain plots, but you can't take corn grain yields from silage plots. Think about that for a while. So we have all 11 treatments listed here. These are the wet tons for silage. These are the dry tons. And then here's the core 8 treatments, which are inside this box, looking at the factorial type of the core 8 treatments. And what you see is there's no significant differences across cropping systems when it comes to silage yields, and there's no differences when it comes to nitrogen rate. Well, we just looked at the grain yields, and we see that we needed at least 220 pounds of N, and maybe even in 1 year, 260 pounds of N to optimize grain production in that study, but 180 seems to do just fine for silage. So one of the messages that we're getting from this study is that, and it was our hypothesis, that we could probably get by with less N when we grow corn silage compared to corn grain. One is we're removing a lot of residue, and the residue tends to immobilize nitrogen. 2, we're blackening the soil. We're taking away a whole bunch of biomass, and when we do that, we're going to obviously have a warmer, drier environment that's probably going to mineralize more N. And this has been shown in other studies, not just this one. Anywhere in the northern Corn Belt in these poorly drained soils, when you remove crop residue, you tend to see this effect of having more N availability. The control plots up here did have a lower yield, and that's why you see some letters that are different here. And this 140 pound rate that was where we grew corn for grain, that did also have a lower yield. That was data from 2023. 2022 was very similar. 2024 was slightly different in that we saw these marginal N rates here for corn grain, the 180 and the 140 being considerably or significantly lower yields. And that resulted in, when we took the mean across N rates and looked at cropping systems, that resulted in the corn grown for grain having lower silage yields. But it's really related to a nitrogen interaction. And that's why this interaction is significant down here. But again, we saw no real yield differences by N rate comparing 180 to 220 when we averaged across the cropping systems. All right, now we'll move in and talk about the water quality information. So in this graph, we have daily precipitation on this y-axis on the left, and that's these blue bars dropping down from the ceiling or from the top of the graph, simulating rainfall from above or precipitation. And this line, or this maroon colored line, is the cumulative tile drainage for the growing season. And that's graphed on the y-axis over here on the right. So I've got a scale here, or timeline, from February, early February through November. Almost every year, January and December have frozen soils and no drainage. Occasionally you'll get a year like last year where it was very mild enough that we had some unfrozen soils in December. But typically following a fall that's relatively dry, you don't see a lot of drainage because usually the soil profile is just being recharged. And that's the way it was in all 3 of these growing seasons. So this was 2022. All of our drainage started, or the tile drainage started to flow in like late April, which is quite a bit later than most years. Most of the drainage occurred in a couple, 3 large events. This event right here, where we got about 2 3/4 inches of rain over a 3-day period, and this event where we had over 3.5 inches of rain over a 2-day period. We had a total of about 7.5 inches of drainage in that growing season. This was 2023. Again, the same scale here on the x-axis. This was the precip on the y-axis, or the upper north, or the top x-axis. You see this flow started here in late March, and then it drops to 0. Well, that's really because we had some flow in certain treatments. And it was due to a ponded water situation. That winter of 2022 into 2023, we had a pretty good snowpack, and then we got some significant rainfall events back here in early February, and we had a lot of standing water in the field in this 2.5 acre area. But it was all primarily in two corners of the plot. And once that started to build up, we saw some flow, tile flow, but it was only in about 10 of the 36 drainage plots. So it ended up skewing the data. So when I decided to, or looked at analyzing it, I actually kept that data separate. And we analyzed it separate, and I actually did not include it in the annual totals. So we went back to start basically from scratch again at this rainfall event, where at that time then basically all 36 tiles were flowing at that period. Prior to that, there was only about 10 or 11 that were getting this preferential flow from where this ponded water was standing. So during this growing season, again, we had almost all of our tile flow occurred in late March through mid-May, and before June 1st, it was all done, which is quite unusual. We had from May 6th to the 15th, we had 6 inches of rain, and we had 5.2 inches of tile drainage. So a significant portion of that rainfall during that 10-day, 12-day period all went out through the tile drains. The cover crop was seeded in September 13th. You can see there was a pretty dry period in there, but then we got some rainfall in late September, and that allowed some good cover crop growth. And we had a total of about 9.5 inches of drainage in 2023. Now, look at the scale here on this y-axis. It goes up to 16 inches of drainage. For 2024, it now goes to 24 inches of drainage. And this is clearly the most that I've ever seen in my involvement in the study, which goes back to the late 1980s. But as you know, as we mentioned earlier, the spring, especially December and December, but primarily January, February of 2024 was extraordinarily dry. From January 1st through March 24th, we only had 1.2 inches of precip. May, we had 7.5 inches of drainage or precip and 6 inches of tile drainage. And in June, we had 12.4 inches of precipitation or rainfall and 9.4 inches of drainage. So 9.5 inches of drainage just in the month of June. So that is an incredible amount and obviously leads to a lot of denitrification and leaching nitrogen losses. You can see it's just pretty much a straight curve. It just kept raining, and you can see that in these bars with some incredibly intense events here in the middle of June where I think our first speaker talked about some of the rainfall intensities where they had 10 to 11 inches over a period of a week or two in June, and we saw that as well. Easily 7 to 8 inches during this period. We did have some significant rain again in early August. We saw a little bit of a blip, but predominantly all the drainage again occurred during that April or late March through June or early July period. So let's look at the nitrate concentrations in this tile drainage water for these 3 growing seasons. So what we have is we have this as a factorial where we're looking at nitrogen rate and then also looking at the cover crop or the cropping systems. We have corn harvested for grain with no cover crop, silage corn with no cover, silage corn with cereal rye, and silage corn with the annual blend. In 2022, the cereal rye cover crop resulted in a nice reduction in nitrate concentrations compared to the silage without a cover crop. It went from 10.7 without the cover down to 6.8, and that was the average for the growing or for the year, the drainage year. The annual blend with the silage was kind of intermediate in between, but statistically less than no cover. And the grain corn was similar to the silage corn with no cover and also similar to the silage corn with the annual blend, but all were significant. We look at 2023, that was the year we had very poor cover crop growth. You see no significant differences among the cropping systems with the silage. The cover crops just did not get enough growth to have any water quality effects. But the grain corn had a lower nitrate concentration than did the silage corns, which was kind of our hypothesis. And then in 2024, where we had very heavy rainfall, very high tile drainage amounts, the greatest treatment was the silage corn with no cover. 25.8 part per million, much greater concentrations than these previous 2 years. The annual blend was not statistically better, just a few, 700 or 7/10 of part per million concentration less. But when we got to silage corn with the cereal rye cover or the grain corn, we see lower nitrate concentrations, and they're statistically lower. And the grain corn system had numerically the lowest, but not statistically less than the silage corn with cereal rye. When we look at N rates, not surprisingly, as others have shown today and others have talked about, wherever you have a higher nitrogen rate, you're going to tend to have greater nitrate concentrations and losses. That's pretty typical. Over these 3 years, we're looking at about going from 180 pounds of N to 220. We're looking at about an 18 to 20% increase in nitrate concentrations in the drainage water. Over here on the right, we have what I call flow adjusted nitrate loss. And it'd be great if all these plots flowed exactly the same, but they don't. Some of them are high flowers, some of them are kind of low. You try to do the best you can when you randomize them and pick them and put them in blocks and replications, but you can never get it perfect. And unfortunately, it's not perfect. But if you take the pounds of loss or load and divide by the inches of drainage, you basically take that variable drainage per plot component out of it. And you get very consistent data that also can show significant differences. And what you see is they very much parallel flow-weighted nitrate concentrations because it's kind of a variant of that. So the lowest in 2022 was clearly the cereal rye, or the silage corn with cereal rye, about 1.55 pounds of nitrate loss per inch of drainage. And the greatest in that treatment in that year was the silage corn with no cover. Go to 2023 and you see these numbers starting to increase a little bit. The lowest one was the grain corn at 1.84 pounds of nitrate per inch of drainage. And the highest again was the silage corn with no cover. And now we go to 2024 and the numbers increase dramatically. And the lowest value is 3.15 with the grain corn, and the highest one now is 5.84 pounds of nitrate nitrogen loss per inch of drainage. And the same results are down here, and there were no significant interactions. So thinking of that, we can also look at nitrate concentrations and how they change during the growing season. And this 2024 year was very interesting for that because we saw dramatic changes and we saw much greater nitrate concentrations than we'd seen previous years. So all 9 treatments are on here in this legend, and I know that's probably really small for you to read, but I'll explain it to you. So down here at the very bottom, this red line with the triangles is the control treatment that only got 4.6 pounds of N. You see how low the concentrations are, but recognize that this is continuous corn, and these plots are in the same area for 3 or 4 years, so this is very nitrogen depleted. The yellow is corn grown for grain, with the closed circles, the filled in circles that are black. Those are the 180 pound rates, and the open symbols, open circles in the yellow line are the 220. So that's the next lowest concentrations from April through May through June, July. Then you see that the green ones are the silage corn with the cereal rye. They started in April about the same place as the grain corn, but they increased fairly rapidly, and then they basically stayed fairly constant throughout May, June, and July. And again, the open squares are higher than the closed square or the filled squares, and that's the higher N rate is the open ones. The blue ones is the silage with the blend of cover crops, and they were similar to the silage treatments that had no cover crop in April, but the silage treatments with no cover increased to even higher concentrations in May, but then declined and actually were lower than the silage with the blend. And that suggests that maybe some of the nitrate that was sequestered in the treatments with the blend cover crop was starting to be released in May and June and actually was lost a little bit later than the treatment that had no cover at all. So the main point here that I want to make, though, is think about the amount of N that was applied in this study and when it was applied. Only 20 pounds of N were applied at planting. So that was about here in mid-May. And you see this huge increase to the left of that when we look at the whole month of May. The rest of the N was side dressed on June 7th. So where did all that N come from that was lost here in May if we didn't really put on most of the N till June? It came from the soil. So it was either residual N that was left in the soil from previous years, or it was just N that mineralized. And likely in that silage system, it was N that mineralized after that silage was removed the previous year in early September. It had all of that warm winter of 2023, 2024 to slowly mineralize N. It became available, it accumulated in the soil profile, and then it was flushed in that really wet May. And we hadn't really put on most of the nitrogen until early June. So any nitrate losses that are over here are probably related to the nitrogen that was applied for that crop, but you really don't see those lines going up anymore. They're pretty much flat or declining. So it suggests that our split application, we really probably didn't lose that much for leaching. It doesn't mean that we didn't lose some through denitrification, because the soil was clearly saturated for long periods of time, and UAN is 25% nitrate when you put it out there. So it certainly could have had some significant denitrification losses. So I wish these cumulative graphs looked as pretty as Fabian's. Fabian's every rate, every treatment looks exactly the same and nice incremental, but unfortunately our treatments, our tile lines don't all flow the same. And this treatment right here in yellow, the silage with the blend has the highest losses, which we kind of expect, but I would also expect the silage no cover, the one in red, to have even greater losses or as high, and they don't. They're kind of in the middle, and that's unfortunately because that treatment actually had significantly less flow. When you total the flow over this 3-year period, it was about 8 inches less flow. Is that related to the treatment, or is it just a fact or a symptom of the plots that they're on? I think it's more a symptom of which plots they were put on. The rest of the treatments all have fairly similar flow, except for these two in particular. But the first year, we had the grain corn had slightly greater total losses. The second growing season, then we start to see the silage corn with the cereal rye and the annual blend start to be greater, and that trend has continued and increased here in the last year. But what is interesting to look at this, and this of course is averaged across the two N rates, but look at how much of our cumulative loss over this 3-year period just happened in this last growing season. This is about 40 pounds right here. This up here at the top is 160. So somewhere between 70 and 75%, depending upon the treatment, of the total loss occurred in one growing season over a 3-year period. And that gets at, like Fabian said too, how challenging and how difficult it is to manage nitrogen in these systems. Now, if we take this and we average across cropping systems and we look just at nitrogen rates, the cumulative loss over that same period, here's our control plot. It's only lost about 18 to 20 pounds. Here's our red, our 180-pound treatment, lost about 120. And here's our green, our 220 treatment. That's lost about 135 to 140 during that 3-year period. But again, the majority of that loss has occurred in this last growing season. So some observations. Good cover crop growth in 2022 and 2023 resulted in good or some reduction in nitrate concentrations from those cover crops. Poor germination and very little growth of the cover crops in the fall of 2022, primarily because it was too dry for growth, but also we just had poor germination and poor establishment of the cover crops. So that year we did not see any benefit to the cover crops when it came to reducing nitrate concentrations in tile drains the next growing season. The 180 pounds of N optimized corn silage yields, which was kind of our hypothesis. However, the corn grain yields required 220 to 260 pounds. And that's important, but it's also another way you can look at this data. And we've seen that it seems like the corn grown for grain is having lower residual soil nitrate before or after the growing season. It seems like it has less nitrate lost, but maybe it's maybe it's an N rate interaction because we have 180 pounds and the 220 pounds N rates, but the 180 is adequate for silage yield. The 220 is probably more than we need. So that increases the losses in the silage treatments, but 220 is probably closer to what we need for corn grain, and that minimizes the potential for losses. So there's some of it is going both ways, but we haven't seen a lot of significant interactions in this study, but there certainly appears that there is something going on there. Nitrate concentrations in tile drainage water were 37 and 21% less with the rye and the annual blend respectively than with no cover crops in 2022. In 2024, only the rye was significantly different, and it was 31% less. So some other states and some other researchers have talked about 60 or 50% reductions using cereal rye cover in nitrate losses or reductions in nitrate. I think this 30 to 35% is probably as good as we've seen here. Maybe we can get a year where we get really good aggressive growth where we can get greater than that, but clearly it's better than doing nothing at all, especially in this silage corn system. In the silage system, nitrate concentrations averaged 18% greater with 220 pounds of N than with 180. And it appears very likely that 180 is probably adequate for corn silage. When I look at the silage quality data, there are some minor small differences in NDF and protein in the grain or in the silage, but those differences are pretty small and insignificant among N rates. I don't think it's enough to justify that extra nitrogen. Nitrate concentrations were a lot greater in 2024 than the previous 2 years, and that could have been we followed a couple of relatively dry years, but when you saw the tile flow that we had in those years, it wasn't like they were really dry. We still had significant tile flow. It just all occurred in the springtime. And nitrate concentrations and flow adjusted losses were less with corn grain when corn was grown and harvested for grain than they were with silage in the cropping systems in both 2023 and 2024. That was not the case in 2022, but it may be an interaction of the two N rates that we've chosen. But it also suggests that this is something that we can use for management in the future as well. With that, I'd like to acknowledge our funding source for this study, and this study will continue in 2025, and that'll be the last year. That was the Minnesota Ag Fertilizer Research and Education Council, or AFREC, and also recognize Kyle Holling. He does a lot of the daily monitoring of the drainage research facility, which is quite time consuming. And Anna Cates has been a big part of this study, and her lab are helping with some of the soil health measurements. And the next time we present this, we'll definitely look into take a deeper dive into some of the soil health, soil tests, and see what we are seeing from those analyses. There's my contact information, and let's see what we have for questions. So this was not necessarily related, this question is not necessarily related to our study, but will N volatilization be higher in extremely dry soil with no snow cover versus snow cover this winter? So N volatilization is driven by where is that fertilizer nitrogen placed. So if this fertilizer nitrogen that was applied was injected, especially if it was injected or incorporated to at least a 3 to 4 inch depth, I wouldn't really expect it to be impacted by the bare soil conditions. Now, if the fertilizer nitrogen or manure was broadcast on the soil surface, not incorporated, left there, then this bare conditions during the winter could enhance volatilization losses. Is it possible to use a slightly lower N rate for corn grain in the year after corn silage? That's a great question. I think if it was a relatively dry growing season and you didn't see a significantly wet spring the next year, that would probably make some sense, but it's something that I don't think we have hardly any data on, and maybe that's something we do need to look at. Any other questions? Any questions from the audience? How are we doing for time? Okay. Well, I'll be here for the rest. Oh,
Back there.
So I'll paraphrase the question. So the question is, do I agree that in our cooler climate, that fall cover crops where we don't get much mineralization after after harvest of grain, where the system cools down, are they less effective at sequestering nitrogen? I think they could potentially be less effective in the fall, but the key is to get them established and carry them into the springtime. And that's when, as you see that spring warm up and you wait until it's time to plant corn, and then, also think about the above ground biomass versus the below ground biomass. And it's very likely that the below ground biomass is having just as much impact on sequestering nitrogen as the above ground and what you're seeing. I didn't talk about it, but we have the data. We got anywhere between 10 and 20 and the most 20 pounds of nitrogen in our biomass. That was all that we could get. Typically, we're in that 10 to 13 pounds of the upper biomass when we looked at the content of nitrogen in it. So that's not a lot, but there's certainly believe that there's probably some in the below ground biomass as well. So when you put it together, it can have an impact. And then we did not put any nitrogen of any kind, including our phosphorus source was triple superphosphate. So there's no other nitrogen that's put out there in the fall. In a traditional farmer's field where you may put AMS on in the fall, you may put on MAP or DAP, you're going to have nitrogen that's going to be put out there in the fall as those fertilizer sources that cover crop could sequester. But in our study, we did not use anything. We didn't put any nitrogen on until we planted, and that was only 20 pounds, and then the rest was side dressed. All right, thank you.
Let's give him a hand.